The promise of artificial intelligence in medicine is transformative, especially when it comes to clinical diagnosis. We see headlines about algorithms that can detect disease with incredible precision. The focus of this session is to explore the hidden pitfalls that can lie beneath claims of high accuracy. I'll discuss the absolute imperative for physicians to understand these tools, to question their outputs, and to ultimately be the ones making the final, informed decision. My goal is to provide a guide for using AI as a critically evaluated partner in patient care. Here's the central issue I'm exploring. What happens when the accuracy score, especially a very high one, is misleading? It's possible for an AI model to boast high accuracy that was achieved through flawed training methods, creating a solution that looks perfect on paper but fails in a real-life clinical setting. I'll examine the ways that can hide underlying problems. This is vital because for every medical professional, the ability to critically scrutinize these AI-assisted tools is no longer optional. Understanding the nuances behind the numbers is absolutely essential when a patient's well-being is on the line. It's easy to be drawn in by a high accuracy score, a model that promises 98 or 99% precision. This is the allure of high accuracy. But we need to approach these numbers with caution. It's easy to see a model with high accuracy and feel a sense of security, but this number can be dangerously misleading. Often, this high performance is due to hidden problems in how the model was trained. In a high-stakes environment like healthcare, this failure isn't just a technical glitch. When it fails to perform on new, real-world patient data, it's a direct threat to patient safety. These hidden problems in a model's training usually take the form of what I call methodological shortcuts. These shortcuts fundamentally compromise the integrity of the model because they create an artificially inflated accuracy score. And if clinicians aren't aware of this, they can be led to make misguided decisions based on what is essentially a false promise. But this responsibility extends beyond the clinic. It falls squarely on the computer scientists and engineers developing these models as well. There can be a powerful temptation to chase high accuracy as a metric rather than pursuing genuine, robust results. Ultimately, everyone involved, from the data scientist in the lab to the physician at the bedside, must be motivated by the same fundamental goal, which is to benefit the patient. We all have to recognize that these shortcuts aren't just technical errors. They can have real negative consequences. In my previous session, I took a detailed look at the how, the specific methodological shortcuts one can take when the primary goal is simply to achieve a high accuracy score. I explored the various ways a model's performance can be artificially inflated, from data leakage to improper testing protocols. The key point to carry forward from that discussion is this. It is entirely possible to use these shortcuts to build a model with a 99% accuracy score that is, for all practical purposes, completely useless. Let's revisit one of the most common and damaging shortcuts, data leakage. Think of data leakage as the model getting an accidental sneak peek at the final exam questions while it's still studying. The result? The model produces what looks like a spectacular accuracy score. But this reliability is a complete illusion. The moment this model is used in a real clinical setting with new patient data it has never encountered, its performance can collapse. This is because it never truly learned to generalize. It only memorized the leaked information. Let's move on to another very common shortcut to high accuracy, overfitting. Imagine a student who doesn't try to understand the subject matter, but instead just memorizes the exact questions and answers from a practice test. When they take that specific practice test again, they'll get a perfect score. An overfitted machine learning model does the exact same thing. It essentially memorizes the training data it's given, including all the noise and irrelevant details. But what happens when that student is given a new exam with slightly different questions? They fail because they never truly learned the concepts. Similarly, in machine learning, when the model memorizes the noise, the random, irrelevant details that are specific only to the training data it was given, just like the student, it doesn't learn the actual underlying patterns in the data. But the moment you present it with new, unseen data from a real patient, its performance collapses, ultimately compromising its clinical utility and your patient's safety. So, how do we actually catch overfitting in the act? We track two lines. One shows the model's accuracy on the training data it's learning from, and the other shows its accuracy on a separate validation dataset. The classic, undeniable sign of overfitting is when these two curves diverge significantly. As I mentioned, I went into the specifics of interpreting these learning curves in my previous presentation. For those of you who have my book, this is covered in detail in Chapter 3. Data leakage and overfitting are the two most common flaws you'll encounter in machine learning training. But the list of potential pitfalls doesn't stop here. There are other, more subtle ways a model's accuracy can be compromised, like cherry-picking results. The name itself gives a clear picture. It's the act of selectively highlighting only the most favorable outcomes from a model's performance. Always demand comprehensive reporting. It means we move beyond a single headline accuracy number and instead analyze deeper metrics like confusion matrices, learning curves to identify overfitting and data leakage, precision recall curves to identify class imbalance, and other validation metrics. That is what enables you to assess if a model is truly generalizable and robust enough for real-world applications. Knowing what to look for is key. In my book, Chapters 8 and 9 are dedicated entirely to this, outlining the specific questions for you to ask when someone presents you with an AI solution they want you to use. Artificially inflated performance metrics do more than just obscure the true effectiveness of an AI diagnostic tool. They pose a direct and significant risk to patient safety. And no matter who assures you of an AI tool's accuracy, they can claim it has FDA approval, they can claim it was peer-reviewed, remain critical. It having someone else approval doesn't guarantee the right questions were asked. At the end of the day, it is your patient safety and your practice on the line. The final responsibility to vet and question these tools rests with you. The ideal way to ensure that machine learning models deliver clinically relevant and reliable outcomes is through external validation. It's the only way to truly ensure that a model hasn't just memorized its training set or benefited from a hidden shortcut. That goes beyond simply testing the model on a small subset of the original data. It involves using entirely new, independent data sets, sourced from different hospitals, different patient populations, and collected with different equipment operated by different personnel. Admittedly, such data sets are hard to come by and often impossible to obtain. Nevertheless, if possible, evaluate the model's performance on the external data set relative to its initial training metrics to identify any discrepancies. While some decrease in performance is expected, even necessary, it shouldn't increase. An excessive drop should be considered a warning sign. But remember, it's not enough to be told a model was externally validated. You have to ensure that the external data set was in fact truly different from the data it was trained and internally tested on. Ask, was the validation data from a different hospital and not just a sister hospital across the street? Was it in a different city or state representing a different patient demographic? Was the data collected and processed on different machines? Were they handled by different technicians? Each of these questions is designed to uncover hidden similarities that could make the external test easier than it should be. Ultimately, regardless of vendor claims, studies, or even FDA approval, physicians remain responsible for patient outcomes. Relying on misleading accuracy scores can have serious consequences, especially if a false negative occurs. Recognizing the difference between a robust AI model and a poorly trained one is quickly becoming a critical skill for the next generation of physicians. Given all the potential flaws and the critical need for scrutiny, where do we go from here? This brings us to the most constructive part of our discussion: the practical strategies you can use for evaluating AI solutions in medicine. A core principle I've stressed in my talks and my book is the need to verify a model's training process for integrity and reliability. This is especially vital when true external testing is missing, which admittedly isn't always possible, then you must depend on the model's learning dynamics to assess its trustworthiness. I recognize that it's one thing to say, verify the training process, and another to actually do it. You might not feel comfortable asking these highly technical questions, and that's perfectly understandable. That is precisely why I dedicated chapters 8 and 9 of my book to this exact problem. In those chapters, you'll find tables with the specific questions you need to ask a vendor or a research team. More importantly, they also outline the ideal answers you should expect to receive if the model is robust and they truly have nothing to hide. Alternatively, if possible, ensure that your team has an expert in this area, someone who has received adequate training on machine learning and its learning dynamics. Question the validity of accuracy metrics you're shown and demand transparency in the methods. But it goes a step further. Insist that the developers of these diagnostic tools include you in the development process. Why? Because only you, the physician, can spot the clinical absurdities that a data scientist might miss. For example, a team might be tempted to include post-diagnostic information in the training data. That is, using information that would only be available after a diagnosis is already made to train a tool that's supposed to help make the diagnosis. Of course, this shortcut would lead to fantastically high accuracy scores, but it renders the tool completely useless in actual practice. You are the only one who can stop them and say, "That's not how this works." You are the essential clinical reality check. So what do we do in the meantime? How do we approach this right now before these kinds of detailed AI evaluations become common practice in healthcare? The answer is that we can learn from the past. We can find a guide for integrating new AI tools by looking at how we've handled new diagnostic information before. For example, a 2017 study looked at colorectal cancer screening and provided a useful insight. It compared two scenarios. In the first, doctors performed a colonoscopy knowing that the patient already had a positive stool test. In these cases, the procedure took longer, a median of 19 minutes. In the second scenario, doctors performed the procedure without knowing the stool test results. In these cases, the colonoscopy was shorter, a median of just 13 minutes. And what does that 6-minute difference in the colonoscopy study have to do with AI? When an AI diagnostic tool flags a potential condition, we should treat it exactly like that positive stool test. It is not a final diagnosis. It is a powerful signal. This positive AI result should alert you, the clinician, to heighten your suspicion. It's a cue to dedicate more time and focus to that specific area of concern, to scrutinize it more carefully than you might have otherwise. The goal isn't to let the AI make the diagnosis. The goal is to leverage the AI signal to enhance your own diagnostic process. This is how we can potentially increase the detection rate of those subtle or difficult to spot conditions, just as the doctors in the colonoscopy study were more thorough when they knew they had a reason to be. Conversely, what do we do when an AI tool suggests a patient is healthy? This is where you must be your most cautious. A negative AI result should never be used as a reason to shorten an exam or to be less thorough. This is how we prevent a dangerous trap called automation bias, the tendency to become complacent and overtrust a reassuring result from a machine, potentially causing you to miss a condition the AI failed to detect. Instead, essentially disregard the negative AI finding and proceed with the full standard of care examination as if you had never consulted the AI in the first place. All right, this is arguably the most important part of this session. So let's summarize it into a clear, practical framework for integrating AI into your clinical diagnosis. First, when an AI diagnostic tool flags a potential condition, do not treat it as a final diagnosis. Treat it as a signal to investigate more thoroughly. This is exactly like the doctors in our analogy who, after learning of a positive stool test, spent more time and care on the colonoscopy. The AI's flag is simply your reason to look closer and apply your own expertise with greater focus. Second, And this is the crucial counterpoint. If the AI suggests a patient is healthy, actively disregard that finding. Proceed with your full standard of care examination exactly as you would have otherwise. This is your most important defense against automation bias. The very real risk of missing a condition simply because the AI overlooked it and gave you a false sense of security. To put it simply, use AI to enhance your focus when a risk is identified, while always relying on established clinical standards as the fundamental baseline for patient care. In other words, the AI is there to make you look harder, not to let you look less. Undeniably, there is a critical balance between innovation and caution in AI-assisted diagnostics. At the end of the day, the ultimate responsibility for patient care does not rest with an algorithm. It rests with you, the medical professionals. This reality necessitates our thorough and critical evaluation of any AI system to ensure its reliability and efficacy before it is ever implemented in clinical practice. And this underscores the urgent need to incorporate these critical evaluation skills into the very foundation of future medical education. And that brings me to why this topic is so fundamental to my own work. My name is Milan Toma, and I'm an associate professor of clinical sciences at the College of Osteopathic Medicine at the New York Institute of Technology. I teach a class at my college where our student doctors don't just hear about AI. They don't just use it as a chatbot. They actually learn how to train machine learning models to diagnose patients. Sure, the primary goal isn't to turn them into data scientists, but by having them build these models themselves, they learn from the inside out. And by extension, they learn the most critical skill, how to recognize a genuinely well-trained AI solution from those with the artificially inflated performance metrics we've spent our time discussing in this session.